Hi, my name is Isaac Ledesma, and today I'm going to be talking to you about CRISPR. Now, before we get into the details of what CRISPR is, I want to get you guys in the right train of thought. So I'm going to give you a scenario, and my question to you is, what would you do? So take a step in time with me, say 10 years into the future. You've now decided to have your first child. You go to the doctor and he tells you, well, why don't you let me modify your child so that one, they are an Olympic athlete, they have the genes of a math genius, or the genes of a musical genius. Moreover, to be more specific, they say, let me give your child the genes that Michael Phelps has, the genes that Einstein had, or the gene that Bach's family had for music. So I'm going to take a moment and I want you guys to answer. What would you do? Would you let them do this? Now, for those of you that said yes, I would ask you, what would you be willing to lose and what would you be willing to risk in this situation? But for those of you that said no, I would also ask you, is this not the same as being a helicopter parent and forcing your child to do, say, 5 hours of piano study, or to do private sports lessons, or to do private tutoring several times a week? So I want you guys to keep that in mind as we talk a little more about CRISPR. So what is CRISPR? CRISPR stands for clustered, regularly interspaced, short palindromic repeats. Now CRISPR is composed of two parts, being the palindromic repeats, which are interspaced. So what does that mean? That means that they are not directly next to each other. There's actually spatial DNA in between each section. The second part is the Cas9 enzyme. You can think of this as molecular scissors. This is the part that actually cuts the DNA. Now, the overall consensus is that CRISPR is an evolutionary trait that bacteria acquired over millennia of war on their arch nemesis, the bacteriophage. The bacteriophage being, of course, a virus that specifically attacks bacteriums. So let's take a look and see how that works. So here we have a bacteriophage that has injected its viral DNA. These Cas genes will then be translated and transcribed to form this CRISPR complex. These spacer DNAs here will then be translated and transcribed to form this CRISPR RNA. So now what it'll do, it'll sit in this complex. Then this entire complex will actually latch on to this viral genome and destroy it. Now you may be wondering, okay, but what if it's a new virus that this bacteria has never seen? Very simple. These Cas genes will then be translated and transcribed to form a new unique complex. This new unique complex will then latch on to the viral genome, make a copy of it quickly, and add it to this CRISPR mechanism down here. So these Cas genes are what are used to create the Cas9 enzyme. These uncolored areas here are the palindromic repeats, and these colored areas here are what we call spacer DNA. So you can think of these colored area, these spacer DNA, as a logbook. These are pieces of all the previous bacteriophages that have tried to destroy this virus or that have been passed on. So this can continue to add spacers until this bacteria either dies or passes it on to another bacterium. Now, this is not the version of CRISPR that we would use in the human body. We have a modified version that is similar, that can work with our immune system. So let's take a look at that real quick. So these two women here, Jennifer Duwadno and Emmanuelle Charpentier, back in 2012 said, well, let's see exactly how CRISPR functions, and let's see if we can modify it to work in the human body. So they said, well, CRISPR is made up of 2 RNA components. Let's cut that down to 1, and then that way, we'll be able to give it the genes that we're looking for, and then we can control it. And of course, I don't know if you've heard about these two women, but recently, in the news, within the last month, they both received a Nobel Prize for this. So what can we use this new version of CRISPR for? Well, there's a lot of things we can use it for. We can use it for genome editing of plants, animals, of course humans, modifying foods, and prehistoric animals. So I'm going to go into more detail about each one of these in their own slide, but I do want to talk very quickly about modifying foods. So China is the leading competitor when it comes to CRISPR. Currently, their government is pouring an immense amount of money into CRISPR, and they have amassed a significant amount of knowledge regarding it. So in one of their studies, they said, well, let's see if we can modify a pig to make it bigger, to make it have leaner meat, and to make it grow faster. They wanted to do this because they wanted to push pigs out into the market as fast as possible, more profit, but not just that, they wanted to meet the high population demand in China. So now here I have prehistoric. So this is more of a new study. Back in 2018, Harvard said, well, let's see if we can go into an elephant, find the gene that closely resembles that of a woolly mammoth, and then let's put that in an embryo, put that into an Asian elephant, and let it give birth to the first woolly mammoth. You can actually read more about this on their website. This study is still in progress. They said it would take approximately 2 years after they found the gene. So if you're interested in that, you can look at that on Harvard's website. So how does CRISPR work when it comes to agriculture? Well, I'm going to give you a little bit of detail on why they're doing this, and then I'm going to talk about the study. So typically, a species that is endemic to an area is typically resistant to the conditions of that area, being animals or temperature fluctuations and such. So we have a species here in Africa called oryza, and this is a very common rice species that they use for supplement, for nutrition. Now, the problem with this plant is that three things: seed shattering, seed lodging, and seed yield. So in areas where there's really bad droughts, this plant won't grow. Or the seed shattering, it will not spread its seeds very well. Or seed lodging, when, as you can see in the picture in the background, the plant leans over. This actually causes a lot of waste. It causes a lot of waste. And even if they did want to get a hold of this plant and use these seeds, with it leaning over like that, it costs a lot of waste. It costs a lot of waste, and it's very expensive to get it, to harvest it. So, and of course, the seed yield is not as much as they want. So what they do typically in these countries is they import rice from other countries. So a lot of the Asian countries do this as well. They will import rice. But the problem with that is that, well, if the species is not endemic to the area, it typically is not resistant to, say, drought or the animals or certain climate conditions from that area. Also, it's very expensive. And these areas typically are people of poverty, and they cannot afford to do that very often. So these scientists said, well, instead, let's use the species that they use, and let's see if we can genetically modify to make the plant stand taller and make it produce a higher seed yield. So what they did is they went into the HTD1 gene and knocked out 3 specific loci: GN1A, GS3, and GW2. So what they did, they took an average weight of 40 grains in grams. So here I have the WT, the wild type, the naturally occurring. As you can see, it's about a little over 0.8. But whenever they knocked out the GN1A, you can see that the seeds were significantly heavier at about 1 gram. GS3, about 0.9, only slightly bigger than the wild type. But this is where it gets interesting. When they knocked out both the GN1A and the GS3, the seed weight rose significantly. Moreover, when they knocked out all 3 loci, the seed weight grew even more. This study provided data to support that, well, we can use CRISPR to modify plants in areas of poverty so that these people don't have to worry about food very often. So let's look at another one that has to do with animals. So here I have one regarding the Pacific white shrimp. So the Pacific white shrimp is one of the main crustaceans that we use in society. This industry currently is worth $15 billion. However, because of this white spot syndrome virus, this industry has also lost, since 1992, about $15 billion. Excuse me. So the problem here is that this white spot syndrome virus, it will infect these shrimp, and one of 2 things will happen with current technology or current testing for this virus. One, it will give a false positive, in which they throw the shrimp out, which is waste. Or 2, it will not give a positive. They will send it out to market, and then they have to recall it. So what they said is, they said, well, let's use CRISPR. Let's give it the gene for this white spot syndrome virus, and let's see if we can verify the presence of this virus. So what they did, they let CRISPR search for this virus on species that they knew were positive, the shrimp they knew were positive, and they wanted to see if CRISPR could verify that. And of course it did. It did not give any false positives. However, what they also did was, well, let's give it some other viruses that are very similar to this virus, and let's see if it'll give us false positives. Now, the results of this study are quite simply that CRISPR gave no false positives. It was able to identify the virus every single time without problem. So let's look at something that's closely related to humans. As I'm sure most of you know, recently there's been a large increase in antibiotic-resistant bacteria. Well, the one thing we don't hear about is that this is actually occurring in fungi a lot as well. So what this study wanted to do is to see, well, how are fungi actually becoming resistant to the medication? How are they doing that? What gene are they creating? Where is it? They want to use CRISPR to search for this gene so that we can make better medications and make these cells more sensitive to the medication. Now, this study is not complete yet. It's still in progress. But they're hoping that with this data, once we find out how a simple organism like fungi do it, we can find out how bacteria do it and how viruses do it. So now I want to talk about something that hits close to home, COVID-19. So this study is very similar to the shrimp study in that the current test will do one of two things. It'll either give a false positive or no positive. So what they did is they had about 50 people who they knew were positive for COVID. They told CRISPR to search for the SARS-CoV-2 gene and use it to verify that those people do have COVID. So they had people that had COVID. They had CRISPR go in and verify these people had COVID. And then what they did is they said, well, let's give CRISPR some viruses that are very similar to COVID, and let's see if it'll give us a false positive. And the results of this study are about the same as the shrimp study. CRISPR did a good job, and it was able to identify it every time with no false positives. So now let's look, well, how does CRISPR compare to its competitors on the market? So here I have some examples of some common genetic tools, I'll call them. One of them being ODM, oligonucleotide directed mutagenesis, TALENs, transcriptor activator like effector nuclease, and ZFN, zinc finger nuclease. So when it comes to time and efficiency, how does CRISPR compare to these genetic tools? Well, let me give you an example. ZFN is one of the main tools that China uses when it comes to modifying pigs. So on average, it takes about 2 to 3 months to modify one pig. That's using ZFN technology. However, whenever they started using CRISPR, that time frame was compressed to 1 week. So as you can tell, the time frame is not only compressed, CRISPR is much more efficient at what it does. Now, when it comes to cost and accessibility, well, how does CRISPR compare? Well, CRISPR is significantly cheaper than all these. Matter of fact, one of the studies that I saw said that you can buy some CRISPR products online right now for about $60. So this brings me to accessibility. If CRISPR is so cheap, I don't know about you, but that makes me worry a little bit about who can actually access it. What if somebody wanted to create a super virus or a super genetic condition that we simply could not find or control? So this is what I like to call risky business. What are the risks of CRISPR entering the market, and how does the public look at CRISPR? Well, as I just stated, what if somebody wanted to use CRISPR with maleficent intent? And this is one of the main concerns in society. Well, who will actually control CRISPR, and can we even control it? So the main thing is, when it comes to who will have access to CRISPR, it is, well, only those with serious genetic conditions. What about the rich? What about when Big Pharma gets a hold of CRISPR? Then what? Sure, it's $60 now. But if you have a serious genetic condition, if Big Pharma got a hold of CRISPR, how much is it going to cost then? What about those of low economic status? What about those in a third world country? Sure, $65 may seem not like not a lot of money here, but in, say, another country, that's a lot of money. Now, my last topic here is cancer. What about those with cancer? So I want to talk a little bit about a study because CRISPR is trying to pave the way for a cure for cancer. So in this study, the goal was, well, let's see if we can increase drug sensitivity using CRISPR. So let's see if we can find the genes that these medications are working at, or let's see if we can find out what genes these cancer cells are using to resist these medications. And let's see if we can make the medications more sensitive, or the sites more sensitive, and make these medications more effective. Now, up until now, I gave you a lot of examples on how good CRISPR does its job. And of course, that was in plants and animals. But now when we're in humans, the result of this study are this. About only half of the medications were even successful. Most of them had no effect. So they had hoped that they could make these drugs more sensitive. They could make them work better. But about half of them didn't work. Now, the scientists in this study said that, well, perhaps we just don't know enough about cancer cells. We don't know enough about CRISPR. We don't know enough about how medications work. And that's probably the reason. And these are all hypotheses, of course. But perhaps in the future, we'll be able to see more. But this is the first study that I'm presenting to you that actually supports that CRISPR is not as effective as what we think. So the next question that society asks is, can CRISPR be controlled? So how will CRISPR deal with the genetic variation from person to person? So although we are similar, genetically similar, we are not genetically identical. How will CRISPR deal with that? If I have one base pair different than you, close to the gene that we're looking for, how will CRISPR deal with that? So From a molecular perspective, DNA and RNA only differ really from this hydroxyl substitution here. Now, DNA, of course, is more stable than RNA. However, scientists thought, well, we should use DNA because it's more stable. We should be using CRISPR only on DNA. Well, this actually turned out to be false. DNA is more stable, but it actually caused further mutations and more off-site reactions. So now we say, well, we should actually be using RNA instead of DNA. So this just goes to show that we really don't know that much about CRISPR, what we thought. However, this is starting to change again now, as we are learning a little more about CRISPR. Now they're saying, well, maybe we should be using DNA. Just something else to think about. Now, the other concern of society is religion. How do CRISPR and religion fit together? Here I have a quote from Catholicism that says, if all humans are created in God's likeness, should we have the power to alter the diversity of ways in which creation presents itself? So each one of you may take this and understand it in a different way, but the way that I understand this is this. If we are created in God's image, and that is right, should we be editing something that is supposedly right from the beginning? Now, Catholicism and Christianity have a very similar view when it comes to CRISPR, in that they don't like it very much, especially when it comes to the editing of the germline, which I'll talk a little more about later. However, Judaism and Islam don't have this view. They believe, well, if God created everything, he created CRISPR. Therefore, it is wrong for us not to use CRISPR to make ourselves better and to help people. Now, as I mentioned before, China is the leading competitor when it comes to CRISPR. And some of their scientists have actually been quoted saying, our religion or our culture is different from that of the Western world. Some of the people that have interviewed this scientist will say, this is a country and a culture that really values science and technology. And I would have to agree that, well, valuing science and technology is very important. These Chinese scientists will say, because they are not bound by this religious bubble, these religious boundaries, that is one of the main reasons that they have made progress, but the Western world has not. An example is this. Here's a study they did on monkeys. So these scientists discovered the circadian rhythm gene, the sleep-wake cycle. And they found it and they said, well, this circadian rhythm gene is also the gene that is more than likely responsible for that creates diabetes and some forms of cancer. So they said, well, let's modify some monkeys, give them these conditions, and then we'll see if we can use CRISPR to make them immune to these conditions. So when it came to their culture, no problems, no complaints. Matter of fact, most of the complaints about this experiment came from the Western world. Most people in the West said, well, monkeys are too smart. You should not be experimenting on them. That's not right. However, even when they did this study, they were trying not to give these monkeys cancer. Because you can see in the picture here in the background, I have 5 monkeys. These were the final 5 clones. These are all clones that they made, and each one of them had one of these serious conditions. But they were trying not to give the monkeys cancer. But in this study, the scientists said that they almost activated the cancer gene on accident. CRISPR almost missed. Again, supporting that maybe CRISPR is not as good as what we think, but it did provide good data in the beginning. So in this same lab, there's a scientist by the name of Ha-Joon Ki. Now, that same lab was working on making monkeys immune to the HIV virus. This scientist here said, well, let's go ahead and move into humans. We're doing so well, let's push into human trials. But they said, no, we're not doing that. HIV is far more complex, and the humans are far more complex. We're simply not ready for that. So what he did, he said, you know what? I'll do it by myself. So he performed an illegal experiment back in 2018. But what he did is he genetically modified 2 female embryos, 2 twins. Now, these people were born, and to our knowledge, they are healthy. He ended up publishing his results, and he got in a lot of trouble for it. The Chinese government ended up giving him a 3-year sentence in prison. Not just that, it led them to permanently ban and make laws against the use of CRISPR on humans. So my question to you is, although this experiment was successful, was it really ethical, what he did? Another question to think about. But why was he worried so much about HIV? Why are we talking so much about HIV? Well, HIV is a very complex condition that is not easily cured. So in this study, the goal was to use CRISPR to see if they could cure this patient who had HIV and leukemia. So CCR5 is the gene that we believe is responsible for the spread of cancer. Of HIV. So people who have a mutation in this gene are typically resistant, if not immune, to some of the main strains of HIV. So what they did is they said, well, let's get this patient who has HIV, let's get CRISPR to modify some cells and make them have no CCR5, no entryways, and then we'll transplant them into this human, and then we'll see how their viral load is affected. So here's a graph that I have here. Total days since the transplantation of the CCR5 null cells. Here I have the viral load. So the higher up we are, the higher the viral load. So at about 150 days, when they transplanted the CCR5 null cells, the viral load was at 0. And it stayed there for about 50 days. Now here we have a huge spike. So the scientists said that in this time, they actually tried another antiviral therapy. And as you can see, it was ineffective. The viral load skyrocketed. But then they started doing the CCR5 null cells again, and then we can see this decline. Now, they weren't able to cure this patient of HIV. But that wasn't really the main purpose. They wanted to see if they could, but they wanted to really see what is the role of CCR5. So they provided even more data to support that CCR5 is the area that we should be targeting so that we can find a cure and make humans immune to HIV. Is that what Ha-Joon Kee did? Well, we'd have to read his study. Now, I cannot talk about CRISPR without talking about eugenics. So now we're going to get into some stuff that may make most of you a little uncomfortable. So, just a quick synopsis. Eugenics was an idea by Francis Galton. And basically, he says, well, those of superior quality should be the only ones breeding. Those of the inferior quality should not be breeding. Of course, we know that this led to an array of problems in the future. Sterilization, and all other kinds of issues. But I want to talk about something very quickly. Something that I call artificial selection versus artificial mutation. So, for centuries, mankind, or humans, have done, well, let me get this plant and breed it with this plant to produce this special progeny. This has also been done in animals. Let me get this breed of horse and this breed, and let me have another new superior progeny. However, if I was to go to the store right now, I would see on a box, non-GMO. Why is it that whenever we see genetically modified foods, we shiver in fear? But whenever we think of artificially mutating humans, no problem. Now, of course, this isn't the overall consensus, but in some areas. Is artificial selection not the same as eugenics? Of course, with all the horrible back history and other ideas, is artificial selection not the same as eugenics? Something for you to think about. Now, the next concern is, well, will we only use CRISPR for therapy and enhancement, or enhancement? So, those who have serious conditions, as I mentioned previously, should have access to CRISPR, of course. I mean, I think we can all agree to that. That if we are bettering the lives of some people, that's a good thing. But should we allow CRISPR to be used for enhancement purposes? This is another question that we'll talk about more here in a minute. Now, let's look at the main issue of CRISPR, and that is germline editing. So what does that mean? That means editing the sperm and the egg. So the main issue with this is that these changes are permanent, and they will be passed on to future generations. So society's main concern is, well, these children cannot consent to the changes that you're making. So should we be making them? What about the autonomy of the child? What about the future generations that say don't want to be 8 feet tall? What about that? This also brings us to, is it even ethical to manipulate humans, period? I guess that's the main concern that we're talking about, right? Is it even ethical? And then we move into two areas of kind of science fiction: designer babies and body dysmorphia. So, is CRISPR going to be so popular one day that one day you're going to go to the doctor and they're going to give you a pamphlet and they're going to say, here, how would you like to design your baby? What traits do you want your child to have? Who knows? Now, body dysmorphia, people who are not happy with the way they look or their body. We know now that there are people that will do immense modifications to their body. Immense. But can you imagine what they would do if they had access to CRISPR? The type of changes that they would do. Now, is this safe? Should this be allowed? Is this even ethical? I mean, we all should have the pursuit of happiness. But is it ethical to let people just manipulate all the genes they want? So next, I want to talk about something I call the rule book, since we're talking about children. So currently, in 18 states, it is mandated that women who are pregnant should know if their child will have some type of genetic condition and how the life of that child will be. However, there are no laws regarding that these women should be told about CRISPR and the progress being made in CRISPR, that perhaps in the future, CRISPR may be able to alter the future of this child's life. So back in 2018, there was a law passed that mandated that women should have all the information they needed to make an informed consent or an informed decision. So typically what happens is, if the doctor does a genetic test and determines, well, this child may have Down syndrome, they have a specialist come in who has typically around 2 years of master's level training. Now, this person will then sit down with the woman, tell her the situation, and tell her what the future will look like. These people are supposed to be unbiased, 100%. That is part of the training. They are supposed to be unbiased. They're not supposed to put their input. But what ends up happening typically is women will ask, well, what would you do? What would you do? If you were in my shoes, what would you do? And of course, you're supposed to be unbiased. But one of the studies showed that typically after about being asked this question about 5 times, these specialists will then start to input their own ideas. Now, the problem with this is that what tends to happen is that these women will usually get an abortion because they fear of the life that their child may have. Now, the problem with genetic abortions is that they lead to a higher degree of stress, a higher degree of anxiety, depression, and PTSD. So how do we deal with this? Well, I mean, it's human error. There's not really any way to deal with it. Now, CRISPR, as we learn more about it, although it is in its infancy, is something that these women should have access to, because maybe one day we'll be able to change these things. So last, I want to summarize everything we kind of talked about. My main question to you, and that I hope that you felt uncomfortable. I really hope that you felt uncomfortable in this study, because this is a very difficult topic and there is a lot of ethical issues. And if you're confused, I think that's a good thing. Is CRISPR ethical? Well, as I told you about, CRISPR is in its infancy, but it has made massive strides when it comes to some cancer research, HIV, food modifications. It has made many strides in there. It is cheaper and more accessible. So although it is dangerous, those who have serious genetic conditions like cancer, maybe in the future we'll be able to find a cure for maybe $100. Who knows? Now, there are many laws against the use of CRISPR in humans currently, although there's starting to be a paradigm shift, and this is starting to change. The overall consensus with religion is that CRISPR is not safe to use on humans when it comes to germline editing. Now, CRISPR has led to an increase in anxiety with genetic conditions. Because we don't know much about CRISPR, it can be a double-edged sword. It can either give these women hope, but at the same time, if it doesn't work, lead them further into depression. So again, my name is Isaac Ledesma. I hope you learned a lot, and thank you for your time.